Welcome to today's lecture. This lecture is on binary search trees. So before we move on to discuss what a binary search tree is, we first need to see how we can represent our binary trees. So in the last lecture we spoke about, we discussed trees, and we also discussed binary trees and the types of binary trees. So binary tree is a tree which has a root, and it has two children, the left subtree and the right subtree. The property is that the number of children every node can have is restricted to a maximum of 2. So you can have 0, 1 or 2 children. So an easy way of representing a binary tree would be the array representation. So how do we represent using an array? So if you have a binary tree as shown here, so this is my binary tree. I have a root, I have a left subtree, and I have a right subtree. So this y and z, for now I have only 3 nodes, but y and z can be subtrees which will be bigger with more number of nodes. So there are two ways I can use a array to store my binary search tree. So if I store them level by level, so first I store this level. In this level I only have x, so that goes in the first location. Then I move to the next level. I have two nodes y and z, and I put them in order y and z. Okay, and as nodes will come in the next levels, I'll keep adding them in the next locations. Okay, another way which is slightly different. Here I started with index 0. I can start with index 1 and leave out this. It doesn't make any difference. It just makes your mathematics a bit easier. Okay, so if I store in this form, this is the first one. If my x, which is the parent, is at position 0, my first child or the left child of x is at position 1. So you can write 2 into 0 plus 1 for that, which is 1. And my right child or the second child of x, which is z, is at position 2. So I can say if my parent is at position 0, the right child is at 2 into 0 plus 2. And if I do it this way on the right hand side, then the parent is at position 1, the first child is at position 2 into 1, which is 2, and the second child is at position 2 into 1 plus 1, which is position 3. Okay, so this is just with 3 nodes. Let's look at an example with more number of nodes. So basically, if you're in this scenario, in the left hand side, if your parent is at position n, the left child will be at position 2n plus 1 and the right child will be at position 2n plus 2. And if this is how you are representing your tree, then if the parent is at n, the left child is at 2n and 2n plus 1. Here it's 2n plus 1, 2n plus 2. Here it's 2n and 2n plus 1. Okay, so let's look at a bigger tree. Here you have a bigger tree with more nodes in left subtree and the right subtree. So again, I will fill up the array equal to the maximum size of nodes that you allow in that particular tree. So again, the restriction is there. If you do it with a static array, then you have to first define what is the size of the array and what is the maximum number of nodes that will be put in the tree, okay, as the tree gets created during the course of your program. Okay, so or you do it dynamically, and whenever you face a shortage of your you have a shortage of space, you can reallocate memory a bigger block and then continue. But then again, you have to see how it works. It should not affect your program. So if you put level by level, so you have I'm using position 1, the right hand side way of doing it. Then level 2 is BC, so I put B and C. Level 3 is DEFG, so I have DEFG, and level 4 is HI. So I have HI. So if you see, I am not putting them continuously. H is at 8. Why is H at 8? The parent of H is D. D is at position 4, so H is the left child. So H is going to be at 2 into 4. And if there was a right child, that would be after H, which is at position 9. There is no right child of D, and then there is no left or right child of E. There is no left or right child of F, and there is no left child of G. So 1, 2, 3, 4, 5, 6. There have to be a space left out for 6 nodes, and then I will be at 15 because the parent of I is G and I is the right child of G. So 2 into 7 plus 1, which is 15. Why we have left this empty? Because the logic which we are following for a tree is that if a parent is at this position, at this particular position, then you will find the left child at this 2 into n, and you'll find the right child at 2 into n plus 1. So you cannot fill them straight away directly here. Okay. Now if you see, if you have a sparse tree, by sparse we mean that not all levels are completely filled, not all nodes have uh, two children. If you see here in this level, in the last level, there are only two nodes. So there are four nodes as parent nodes, and only two nodes have children, and these two nodes have only one child. So it's a sparse tree in that sense. So if it's a sparse tree, you will have empty spaces like we had here in between. So although this implementation is very easy, this problem where you have a lot of empty spaces, it kind of creates a wastage of space, and it would be more efficient if we do the same using pointers. Okay, so this works well for those applications which use complete binary trees. We'll see later on when we do heaps. Heap is a complete binary tree with some exceptions and some properties. For that, it's easy to use an array, and you'll see how we can define that array also dynamically so that we can reallocate in case we run short of space. So because of this issue of this empty spaces in the array, it's better for such kind of trees to be implemented using your pointer method. So this works well for full and complete binary trees, like I said. So, and you'll have empty spaces in case you do not have a complete tree. Okay, so how do we do the same thing using the linked list representation? It's not actually a linked list because a linked list has one or two pointers and linked list is linear, but it is a similar representation to linked list. So in linked list, if you had a node A, it would be connected to a node C using a pointer. Okay, let me draw it here. So it would have been like this. Okay, but now in case of a tree, depending on the number of children, there are two pointers that leave the node, so you can either take the left direction or you can take the right direction. So if you see here, we will define a structure called a tree node. We have a linked list node, we have a tree node. What is the definition of the tree node? You have an element. For simplicity, we take only an int so that we can work easily. Then you have, it is a self-referential structure again, but this time just like a doubly linked list, we have two pointers. In case of a doubly linked list is linear in the sense that you either go forward or you go backward. Okay, so in case of a tree, you either go left or you either go right, and in each of the choices, whether you take the left or the right, you again have two choices. So it's not linear, it becomes non-linear. So just like our linked list, we create a structure and we create this is the start pointer, we call it the root because root is the first node of the tree. It's like the entry point to the tree. So how do you make a tree? Okay, making a tree involves creating the node. Just like adding a node to the linked list, we first declare memory for that node, and then we populate the node with the element and we fix the pointer wherever it has to point to and whatever is pointing to it. So similarly in make tree, you first define a pointer of the type tree node. This pointer, you use malloc for memory allocation. You can only also do typecasting here. I've not done that. You put the element if you had to make the tree using x. Okay. Now when I say make tree, I'm actually making the tree node. I'm not making the entire tree. So whenever I'm given something, some element to add, when I call make tree, this function will give me a node with that element, and its left and right pointers will be set to null. So what I have to do after this p is returned to me, I have to make if there is an existing tree, I have to make that existing tree point to this node. Whether this node is going to be the left or the right right child of a particular node, that I'll do there. Okay. So this is basically, it just gives you a node with its left pointer and its right pointer as null, and it also gives you this node, and this node is populated with the value x. Okay. Now if you have to add to the left subtree, so for example, for now, till you go to the binary search tree, you'll know how we will know where exactly we are going to add a node. So for example, you know the location, you have gotten to the point or to the node, and you have to add this x as the left subtree or as the left child of this particular node. So you pass the pointer. Most of the time we pass the root, and if we arrive at the correct location, and then that correct location is p. If p is null, you don't have any node to insert because you cannot put something as a left child. If it's empty, then nothing goes there. If you have to add this node on the left side, so if there is an existing node on the left side, you cannot add something there. So you have to look for an alternative location. So if there's already something in the node, you print invalid. Else you put this x node in p2 left. Here you see make tree. This make tree will allocate memory for a node. Put x in that, put the left and the right. Basically it initializes the node. It does this for you. Okay. Puts x here, and this left and right is null, and whatever the address, this p, that is returned, and that is put in p2 left. This p is the p in this function. Similarly, if you know that you have to add something to the right of a tree, again you check if p is null. If p to right already has something, then it's an invalid insertion. Otherwise p to right is make tree x, and this is your make tree that we did in the beginning, which makes this for you. Okay. Now what I want you to understand before we move to binary search tree, that whatever you do in a tree, it is recursive in nature. Okay. So understand that whenever you have to do something in a tree, if that that function or that whatever you want to alter in the tree, if that is not to be done at the root, it either has to be done in the root of the left subtree or the root of the right subtree. And if not there, it either has to be done to the children, in one of the children of the left subtree or one of the children of the right subtree, and so on. Okay. So for example, you have a directory and you want to list all the subdirectories and all the in that chain. Okay. So a directory can have any number of directory is a folder. Any folder can have any number of folders inside, and then each of these folders can have any number of folders inside. So you want to print and see how it looks like, the tree structure of this. Okay, the hierarchy, which is the main folder, what are the subfolders, and what are the folders under these subfolders, and so on. So we call a function called list directory d, we pass this directory and we call another function list directory D with 0. 0 is the depth. So your first folder is at depth 0 or level 0, just like our root. It is the root folder. In many programming applications, you'll see when you move around folders and you say, I am at the root. In Linux and Unix, you usually see, I am at the root directory, and then I go to other directories from there by using some commands. So I call this directory D with a depth of 0. If D is a legitimate directory entry, then I print the name, okay, and its depth. Okay, that's here. And then if D is a directory, it can be a file. So if D is a directory, then only I have to call the same function list directory for each of the children of D with a depth of depth plus 1. So it will call list directory. For example, I have this directory and I have 3 subdirectories under it. Then this is your D. So I called this list directory on D with depth 0. Then for each child in a for loop, I'll call this function on the first child with a depth of 1. Then I'll call once I return. So when it goes inside, it will list everything that is under C1. Then it'll come back here to C2, that is at C2, that is at depth 1 again. Then it will go recursively down under C2 and print everything, and similarly it will go to the third child and return back from there to here. Okay, so everything that you do in tree mostly will be done using recursive functions, because we are dealing either with the root of the tree, or we are dealing with a whole left tree or a whole right tree. Now we come to our binary search trees. Binary search trees, as the name implies, they are used for searching. And why they are used for searching, you'll get to know in a while. Normally, if I give you an array with a list of elements and I ask you to search a particular element in the array, so what is the way you would do it? A basic way is that you go from 0 to n minus 1 and look for that element. In case your array has elements that are stored in a sorted manner, let's say ascending order or descending order, then you can do something like you can say binary search. We find the middle and we see what element is at the middle, and if the element you are looking for is less than that, then you search the left part of the array, or you search the right part of the array. Okay, only if your array is sorted. So in this case, in case of binary search trees, we don't keep the elements in a sorted manner, but it still makes our searching easier. So every node in a binary search tree has a key value. So for simplicity, when we talk of binary trees, the element in our node is the key value, and that is what we will use for our search purposes. And we assume that there are no multiple values. So you cannot have a repeated value. That is the assumption, because if you have repeated values, the whole logic of binary search tree gets flawed. So what is a binary search tree? For every node in the binary tree, it is a binary tree. It can have at the most 0, 1 or 2 children. Every node can have either 0, 1 or 2 children. How are the values arranged in the tree? The key value, if you have a root node, all the elements in the right subtree will be greater than the root node, and all the elements in the left subtree will be less than the root node. And the same definition applies to the subtrees. So in the left subtree, which is less than the root of the left subtree will have all smaller values to its left and all bigger values to its right. So for example, you see this example here. This is the root 6. Okay, 8 is greater than 6, so 8 will go automatically to the right side. 2 is less than 6, 2 will go here. 1 is less than 2, so it's on the left side. 4 is greater than 2, it's on the right side. 3 is greater than 2, but 3 came after 4, so 4 was here, so 3 should go on the left side of 4. So on the right hand side, when you see the 7, it cannot be here because 7 is greater than 6. So it should have been in the right subtree of root, not in the right subtree of 2. Okay, if this top part was not there, then this was a perfect. The left subtree itself is a perfect binary search tree. But if you put the 6 and 8 here, it's not right because 7 has to be on the right side of 6. So 7 should have been like this here. 7 is less than 8, so it is on the left of 8. 7 is greater than 6 and 7 is less than 8. So how do you make a binary search tree? You go step by step. You just have to follow the paths and see where your element can go. So when you have 10, you have nothing in the node. You only have this basic 10 value. So you make a node out of it and put 10 there. First element. So your tree is basically created now. When you get 4, how do we decide where to put 4? We compare 4 with the value 10. So if 4 is less than 10, then 4 should be the left child of 10. If there is no left child of 10. Okay, if you saw in the make tree, if there is already a left child for 10, then you will not be able to add 4 as the left child of 10. We'll see in a while. Okay. Then here, when 6 comes, 6 is less than 10. So 6 cannot be the left child of 10 because it's already occupied. So we just follow this path. Okay, 6 is less than 10. Let's come here. You reach the root of the left subtree. Okay. Now this left subtree has 4. You compare your 6 with 4. 6 is greater than 4, so it goes into the right side of 4 if it is empty. Okay. Then 3 comes, so we compare 3 with 10. 3 is less than 10, we come here. We are sent to the left subtree. So when you come to the left subtree, apply the same logic. Compare 3 with 4. It is less than 4, so it goes to the left subtree or the left child if it is empty. If not empty, we will send it to the left subtree and then see where we can put that 3 in. Okay. So similarly, 12 comes. You compare 12 with 10. It is greater, so we put it as the right child, as 10 to right is null for now. Okay. 14 and 2. So 14 comes. 14 is greater than 10, so we send it to the right side. Then we are basically sending it to the right subtree. So when 14 comes to the right subtree, it compares itself with the root. The root of the right subtree is 12, so 14 goes to the right of the root of right subtree. And if that is empty, we put 14 there. Otherwise, we recursively call the same procedure. So then 2 comes. We compare 2 with 10. 2 is less than 10, so 2 goes to the left subtree. Left child of 10 is occupied, so we call the same you can say the same add procedure on the left subtree. That's why trees are recursive. So you compare 2 with 4. 2 is less than 4, so you see if you can put 2 on the as a left child of 4, but no, that is already occupied. So you call the same function. You send 2 to the tree, which is actually the left subtree of 4. So you compare 2 with 3, and 2 is less than 3, so it goes to the left child because that is empty. Okay. If you see, the sequence of elements will determine how your tree will be created. Okay. And you have no control over the structure of the tree, in the sense, it's a binary search tree. You'll program it in a way that you will have a left child and a right child, but based on the value, the elements will find their own places. And sometimes, let's say if I ask you or tell you that you have to build a binary search tree with these following values 1 2 3 4 5. So once you do it on your notebook, you'll see that this is what gets created at the end of it. So 1 comes, 1 becomes the root, 2 comes, 2 becomes the right child, 3 comes, 3 is greater than 1, greater than 2, it becomes the right child. and so on. So if you see, all the left pointers for all these nodes are empty. There are only right pointers, and it essentially looks like a linked list, which we have drawn in a slightly slanted way. Okay, so if you come to search for, let's say, 3 here, or let's say 5 here, you will have to traverse all the way to the end of the list. Okay, so it essentially, at that point of time when your tree is not balanced, we talked about the balanced and unbalanced tree. Balanced tree is where your left and right subtree have a maximum difference in height of 1. So either they are at the same level, or they are 1 above or below the other one in terms of the height. So if you end up with a structure like this, your traversal time will not improve. We'll see in a while why we use binary search tree and how it makes our life easier. So whenever you come to a binary search tree, you start at the root. Okay, so if I tell you look for the element 6, okay, because of the property of the binary search tree that 6 is an element which is less than 10, it will of course be in the left subtree. So at the first step itself, you are discarding the right subtree for searching. So there's nothing, obviously 6 is not going to be in the right subtree, so you don't have to search and compare your 6 with 12 and 14 to see whether it's there or not. We know it's not there in the right subtree. So this whole right hand side is kind of cancelled out. Then you come, then we call the same search function for 6 on this left subtree whose root is 4. Then we say, okay, 6 is greater than 4, so it's going to be in the right subtree of 4. So we again call search on the right subtree of 4 with the element 6. And we see 6 will match with the root of this right subtree, and we found 6. So one comparison here, second comparison here. Okay, let me see. Okay, this is your first comparison with 10, second comparison with 4, and third comparison with 6. And 6 is what you were actually looking for. Okay, so this is how it reduces your search time. If all these elements were stored in an array without being sorted, then you would have to search through entire, there are 7 elements, you would have to do at least, at the most, 7 comparisons, and least would be depending on the position of 6. Okay, now we want to implement this binary search tree using pointers. Okay, so we already defined the structure for a binary search tree. For a tree, basically the T node structure, it has an element, it has a left and a right child. Okay, so we do a type def struct T node search tree. We call our tree as the search tree, and then we start writing the functions for that. Now our first function is make empty. So what does make empty do? We'll see later why we are writing a function to make a tree empty. So if I send a node to this function, it sets, basically it sets its left and the right subtree as null, and it frees this node. Okay, but for that t has to be a non-null value. Okay, so if t is not equal to null, I call make empty recursively on the left, because there are many nodes under a particular node on the left side. It's not just you free t. If you free tree, all the nodes in the left subtree, they are still allocated. You haven't told the system that I'm freeing all these nodes. They can be taken back and used for something else. So we do this free, what free we used to do in case of linked list, we are doing it recursively for every node in the left subtree. Okay, and once this recursive call is finished, then we actually use the free function that is available in C to free a particular node or return this back to memory. Okay, and you return null. Okay, now just now we were looking for 6 in the search tree. So this is a function that will do that for you. Okay, we'll see how insertion and deletion, that's a bit more complicated, so we'll do the easier ones first. So you send the, normally for searching a particular element in a tree, we send the root of the tree to the function, and we are sending x. So we were looking for 6, so we'll send 6, and we'll send the root address. So if root is null, there's nothing to search, you return back null. Okay, now what do? We check if our x is less than the element in the root node. If x is less than that, we call find the same function with the value x, but on the left subtree. T2 left is the address of the root of the left subtree. And if T2 element is less than x, which means x is greater than T2 element, you call the same function on the right subtree. And if it's neither less or greater than, then that means it is equal to, because there are no repetitions in case of a binary search tree. If 6 is not less than 6 or greater than 6, which means it is equal to 6. So we are returning the node address in which 6 is present. We're not returning 6 here. So we're returning a pointer. Okay, so this should be search tree star t here as well. Okay, I forgot to add that here. So most of these functions, they return a pointer, so that should be added here. Now if you look at your trees, let's go back here. Okay, so this is your search tree. If you look at it, whenever, if I try to put -1 next, -1 is less than 10, it's less than 4, it's less than 3, less than 2, so it will be on the left side. So on the extreme left side, if you start at the root and take only the left pointers till the end, you will find the least element in the binary search tree. And when you start at the root and keep on taking right, you will find the maximum element of the binary search tree. So minimum element in a binary search tree lies on the leftmost side. So you start at root, take left till you hit a null, and the last node whose left pointer is null is your minimum. And similarly, you go right all the way to the last node, and that is your maximum. So you can recursively do that. If t is null, you return a null. If t2 left is equal to null, that means if you have hit the last node, the left of the last node will be null. If there is no more left after that, then you return t. Otherwise, we call find min on the left subtree, and so on. It will continue calling on the left subtree till t2 left is equal to null. Okay. Similarly, you can do maximum. This function is recursive, so instead of t2 left, everywhere if you replace it with t2 right, it gives you the maximum. Find min again returns the node that contains the minimum element and not the element. So we can do it iteratively, just like this. So if t, just like we do in a linked list, we'll do if t is not equal to null, I'm finding max. So while t2 right is not equal to null, when t2 right is null, then I stop. Okay, and I keep on doing t is equal to t2 right. So I keep on taking the right path, and once t2 right is null, that is the t I'm looking for, and I return that. So when you take the orange lines, you're taking all the left pointers from the root node. You will eventually hit the last node, which will be your least element, and if you do that on the right hand side, you will hit your maximum element. And you can do it both iteratively and recursively. I've done one recursively and another one iteratively. Okay, so Now the main two functions in a binary search tree are insertion and deletion. Okay, so how do you insert in a binary search tree? The logic is same. When I get an element, I try to see whether it is less than the root or greater than the root. If there's no root, then this element becomes the root. And if this element is less than the root, I try adding this element in the left subtree. So I'll recursively call insert this x in the left subtree. Till I find an empty location at the correct place, I will add it. So this is how it goes. If your t is null, that means either it's the root that is null, or in one of the recursive calls you hit a null t. So what you do is you create a node using malloc. If t is null, it's a good practice to do this. After malloc, if your t is still null, that means the system is not able to allocate memory to you. Either it's out of space or there's any other technical error. So it's a good way to good programming practice to check if t is equal to null. Okay. If it's not null, then you put the element x in t. You set the left and the right pointers to null. You can also call make empty for this x, and that will do the job for you. Okay. Else, if your x is less than t2 element. Okay. Now, before I go here, this is your if and this is your else, and this function returns t. So it returns, let's say if it hit a null, it will create the, obviously when we are inserting we have to create, eventually it will come here. Even if I am making recursive calls, it will create this node, and obviously it will not go into else, it will return this t. So when I call insert x t to left, if x cannot be added at the root location, x is less than the root element, I call insert x in the left subtree. Okay, and whatever, for example, the left subtree is empty, so whatever pointer is returned from this insert function, this will be, the value would be sent to t2 left. Okay, it will be linked here. And if x is greater than t2 element, your x will be inserted in the right subtree, and whatever t value, it will come here in t2 right. Now this t2 right is not always root to right. It can be, since we going to have many recursive calls, it will be that recursive call in which t2 right was null. Okay, because if t2 right was null, if I call insert x in t2 right at some level of recursion, t2 right is null. Okay, this is null. So when this next time this function is called, this is null. So a node will be created here, and that value will be returned, and that value would be put in t2 right. So it will go to the exact location where this element has to be added based on its value. Then it will put it at the right place by checking if t2 right is null, that is where it has to be added. Otherwise, it will keep on finding the correct location using recursion. So you cannot have duplicates. So for example, you have to add 4. Okay. So 4 is less than t. This is your t initially. 4 is less than t2 element. So I call insert 4 in t2 left. So this becomes my new t. And in this new t, which is 5, 4 is less than 5. Okay, 4 is less than 5. So I call insert 4 in t2 left. What is t2 left here? It is null. Okay, when t2 left is null, in the next recursive call, a node is created and you put 4 inside that. You return that address of t2 of this insert call and put it in t2 left. So the node that was created there is added here, and 4 is already inside that, so This is how addition takes place. Similarly, if 14 is to be added, 14 is greater than 10, so you call insert 14 in this. Then 14 is less than 15, so again 14 is less than 15, you'll call insert 14 in 15 to left. 15 to left is empty, a node will be created and that value would be put in 15 to left. Okay, so you have to do it a bit because the recursive calls involved, you cannot exactly see how it works, but your t changes with every call. Just mark your new t's and see where the node gets added, and it always does it correctly. It always finds the exact location and obviously an empty right or left link where the new node is added. Now coming to deletion. Again, to do anything in a linked list, sorry, in a binary search tree, you have to get to the exact location, see where the element is, or where the element should be based on the binary search tree property, and then you, for insertion, you put it there. And for deletion, you actually get to the node and delete it. Now, a node, for example, you have to delete 10. So when you delete 10, 10 is a root node. So how do you manage the left and the right subtree? They have to go somewhere, as in where should 15 go? Okay, you cannot just add 15 directly somewhere, but you have to see that the binary search tree property is maintained. So let's go step by step. If your t is null, you'll have an empty tree. That means you cannot delete any further. So maybe what you are trying to delete is not there and you have been calling recursively the left or the right subtrees, and when you actually you hit a null end where you don't find the element, that is an empty tree or an empty subtree, so you can just display an error. If x is less than your root, we start with the root as t. If x is less than that, we call delete x on the left subtree, and just like we do for insertion, we make recursive calls. So we call it to the left, we call it to the right in case of the value being less than or greater than. Now if it's not less than or if it's not greater than, it is equal to. So that means if we go into this else, we have actually found the node. Now if that node is, let's say, 15, 15 doesn't have any dependency, in the sense 15 doesn't have any children. Okay, so you can just say make empty 15, which is basically free 15, and you're done. Okay, or it is possible, let's say we have 15 and we have a left child. Okay, even in this case it is easy. So this is the case for 0 children and this is the case for 1 child. If 15 has 1 child, this child can straight away, whether it be the left child or the right child, it can straight away come up and take the position of its parent. If there was a right child, either of the left or the right child, it will just come up and take the position of its parent. So having 0 or 1 children is easy. So what we do is, when we find the element to be deleted, we copy its address in a temp variable because we have to free temp. Okay, or you can, this is just freeing a node, so we can just do free temp. If t to left is null, t is equal to t to right. If there is 1 child only, maybe t to right is also null, so t will be set to null. Okay, but we have already copied this here, so we can do free temp of the actual location. So when it's set to null, it's set to null either this way or that way. We are returning this t, and where are we returning it? To the place where maybe you had a call if x is greater than t to element. Let's say 15 is greater than 10, so we called 15 is greater than 10, we call delete 15 from this subtree whose root is 15. Okay, it was t to right. Okay, so we are calling the subtree which is at 15, and we are calling for deleting 15. So what is this t here? T is your root node 10 and t to right is 15. And what is this 10, sorry, t to right? This is actually 10 to the right side. What is 10 to right? Which is 15. So we are calling delete 15 on 15. And in the next recursive call, because 15 is not less than 15, 15 is not greater than 15, 15 is equal to 15, and 15 has only one child, you copy the address of 15 in temp, and then 15 is set to null, and we are returning that null here. Okay, we are freeing the value wherever 15 was, and we are returning that null. And where does that null go? The null is the replacement of this recursive call, and that null goes in 10 to right. Okay, and if there was one child, that would be set appropriately here, and that is the value that will be returned. So in case 14 was copied at the place of 15, then the address of 14 will go in 10 to right. Okay, so let's do another example here. So we just did for 0 and 1 child. Okay, let's go, we'll do first, let's do for 0 and 1 children. So when you delete 4, you will keep calling the delete function till you get to the t where t to element is equal to 4. So once you find that, how will you get to know whether it says 0 or 1 children? If both left and right pointers are not null, that means it has 2 children. We haven't covered that case yet. So if it has only one child, so t to right is null, so we make t equal to t to left. So t is copied, this t is copied in temp, and then t is equal to t to left. Now this becomes the new t. This is freed because this is copied in temp, and this t is returned in the previous recursive call where the parent of 4 called t to right. So t to right was equal to delete 4 from t to right. So it became t in the next recursive call. So 2 started pointing to 3 now after this function return. Okay, now this is the case with one child. So even if this child 4 had a right child, that would be copied, and actually the value is not copied. The address value of the node 3 is copied in t, and that is set as the right pointer of 2. Okay, so we don't just copy 3 on 4. That happens when we have 2 children. We'll just get there in a while. Now let's say you have to delete 2. Now when you actually reach here, what do I mean by reaching here? When t2 element, when you see 2 is less than 6, okay, when you see 2 is less than 6, you call delete 2 on 6 to left, which is the left subtree. Now 2 is not less than 2, 2 is not greater than 2, so 2 is equal to 2. That means I have hit the exact node which I want to delete. Now I want to delete 2. I check how many children it has, and when I check, the t to left or 2 to left is not null, and 2 to right is not null, so I have 2 children. So what do I do when I have 2 children? I cannot straight away say 2 is equal to make this t point to 5, because if 5 comes here, 3 is the left child of 5, okay, and you already have 1 here, so that cannot happen. So this is what we do. Once you find out that your node has 2 children, there are 2 ways of doing it. We'll do this way. We find the minimum in the right subtree. Okay, we find the minimum in the right subtree. Why do we find the minimum? if I take the minimum from the right subtree and I put it instead at the place of 2, rest of the elements in the right subtree will still be greater than this minimum. So for example, here, what is the minimum of 5, 3 and 4? It is 3. If I take 3 here, just for now, if 3 is here, 5 will still be greater than 3, and this will suffice the binary search tree property. We'll see later how we manage this here, but for now we copy the value 3 here. We do not do the pointer changes that we did in the case of 0 or 1 children. We copy the value here. So what we do, in T, which had 2, which we are going to delete, I am putting temp to element. Temp to element is the minimum element. Find min returns the node address which has the minimum element. So I take the element there and I copy it on that. And once I copy it, once 3 comes and sits here, there is a duplication in the tree. So what I do is I call delete 3 from the right subtree. Okay, so I say, okay, delete now this 3 from the right subtree. I know it came from the right subtree. There is a duplicate copy there. I have copied the value of 3 here. So I'm not doing any pointer changes in this node. I am just copying the value 3 here. Now I know there is a duplicate 3 in the right subtree. So I will call on deletion for 3. So again, the same procedure will be followed. Eventually, when you keep doing this, you will hit a node which is either 0 children or 1 children, and that is easy. That we have already covered. So 3 has 1 child, so I will copy 3, the address value of 3 in temp, and I will send this value back so that 5 to left becomes 4 and 3 gets deleted. Just like we did for 0 or 1 child. So 3 is a node with only 1 child. It will be taken care of like that. Okay. I have just written some comments here. Now, like I said, there are two ways of doing it. Either you take the right subtree and find the minimum, or you take the left subtree and find the maximum. So here the left subtree is a little smaller. So let's say this is our tree and I want to delete 6. So what I do is I take this entire left subtree. What is the maximum of this tree? It is 5. So if I put 5 here instead of 6, the property of the binary search tree is retained, and then I call for deletion of 5 in this left subtree. And if you see, now once 5 is here, this left subtree here, you have to delete 5. So when you reach here, 5 has 1 child. So no, sorry, this is a wrong. There is duplication here. So let's do it on this side, on the left side. So 5 is here now, and I want to delete 5 in the left subtree. So once I reach to 5, 5 has a left subtree. It doesn't have a right subtree. So when t to right is equal to null, t is equal to t to left. So this address is what becomes t, and this is what is returned to 2. So 2 will point to 3 and 3 will point to 4. It will be on the right side. So either find min on the right or find max on the left. Okay, so this is your deletion in a binary search tree. So it's better that you do take some simple values, create a binary search tree, follow the code that is written here, and do insertion and deletions, and kind of keep a copy of the t values in each recursive call. You can write t6, t5 to denote that now I have called 5 as the root node, so t is actually 5, and then you can trace so that you can understand this properly. Okay, so now in the last lecture we discussed the tree traversals. Okay, so you have tree traversals. You can traverse in order, pre-order, or post-order. So now if you want to print your tree, so we can only print our tree in one of these three orders, and the functions are pretty simple. Like you did it by hand, we said if you have to do a postfix traversal of the tree, a post order traversal of the tree, what you do, you first print the left subtree, then you print the right subtree, and then you print the root. So same we follow in our recursive calls. So post order search tree, if t is not equal to null, we call post order on the left subtree. So again the same order will be followed. Post order on the right subtree and print the root. Then these are recursive calls. They will print their subtrees in post order again, because they will call this function and this will again print it in post order. So like I said, when you say post order, so this is in order, post order, call the left subtree, call the right subtree, print A. Okay, this further call the left subtree, which is, it will actually call the left subtree dt, and dt itself is null, null, and d. So there is nothing in the left subtree, nothing in the right subtree, so d will be printed, and the right subtree b is the root of the left subtree, then F, G, C, and A, and then this as the final post order. Okay, so same case for in order. In order, you first print the left subtree, then the root, then the right subtree, and then you return. So the printing will be taken care of. Pre-order, print the root first, print the left subtree, print the right subtree, and then return once all the recursive calls are done. Okay, so your there are two more pages to this after pre-order, post-order. So we also want to know at any particular point of time, we are not talking about balancing trees right now. So for now, you'll just create simple binary search trees, whichever structure they form based on the values you give. Then you have, how do you find the height or the depth of a tree? So how we do that is again recursive. So if you can find the depth of the left subtree or the right subtree, whichever is greater, plus 1 would be your total height or depth of the tree. So what we do is we call max depth. If t is null, you return 0. If it's not null, the left depth. Okay, it is the depth of the left subtree, and right depth is the depth of the right subtree. Okay, once it returns back, these are again recursive calls. If left depth is greater than right depth, okay, you return left depth plus 1. Whichever is greater, plus 1, that is the path from root to the left or the right subtree, is going to be your height. So you will return that. And if t is null, you return a 0, so that takes care of the mathematical part. So similarly, if you have to count the number of nodes, if t is null, you return a 0. Otherwise, what is the count? Count is c. We start with 1. If there is a root, there is at least one node. If there is no root, we'll return a 0. Okay. If there is a root, then you do 1 plus what the number of nodes in the left subtree, and whatever value you get for c in the previous line, that plus count t to right, and then you return c. Count t to right, it is a recursive call. It will call and it will do the calculations. Similarly, if you want to find the leaf nodes, if t is null, you return a 0. If there is only one node, which is the root node, so that means the left and the right subtree is going to be 0, then you return 1. Otherwise, you return t2 left plus t2 right. Okay, and the value that is returned here, this will be 1 only if the left and the right child of these nodes is 1. Sorry, the left and the right child of these nodes are null. If both are null, then you can return a 1. If they are not null, you don't return a 1, you return a 0. So it's a leaf node, you will return a 1 only when it's a leaf node, which means the left and the right subtrees are null, or the left and the right pointers are null. So there are many more functions you can write for binary search trees. You can count the number of internal nodes. So you know internal node is one which has at least one child. So I haven't done that. So you count a node only if it has a child. 1, 2. But if it has zero children, then you don't count it. Okay, so I'll leave that one as an exercise for you. Okay, so I'll upload these and I hope you will go through this, and this will be very useful because it pretty much covers everything. It's mostly recursive, so like I said, do some dry runs with some sample trees that you build. The sample trees, you can mark the nodes with T as well as the value in the key to see if you can actually replicate the coding part. You can easily build a binary search tree using your pen and paper. I give you a sequence of values and you put them in order and make a binary search tree, but see how you can do it, how that is actually followed in the code, both for insertion and deletion, and you can try counting or printing for the same. So do it by hand manually and do it by following the code. Okay, so this is your end of binary search trees. The next in line is heaps, which is again a complete binary search tree with some different properties, different structural properties, and order properties. So that will be your next lecture, and that will cover the basics of trees that you have to do in this course. All right, thank you.